Section 15.5. Large integer multiplication. Large integer multiplication is similar to matrix multiplication in one important sense. In matrix multiplication, each element of the product is the sum of products of two elements, one from each matrix. In large integer multiplication, each digit of the product is the sum of products of two digits, one from each large integer. Anyway, that's my rationale for putting this topic in the matrix chapter. A 128-bit block can be viewed as 16 bytes or as 16 base 256 digits of a 128-bit integer. If you multiply two such base 256 integers, that involves 256 products and 256 additions, including the carries. It's a lot faster if the language you use allows you to multiply two 32-bit unsigned integers to get a 64-bit unsigned product. Then you need only 16 multiplications and 16 additions. If the language allows multiplication of 64-bit integers with 128-bit products, it's even simpler. There are faster methods for multiplying very large numbers, such as the Karatsuba and Toom Cook, but the benefits of these methods for multiplying 128-bit numbers or even 256-bit numbers are too small to make these worthwhile for present purposes, so I will not get into the mechanics of large integer multiplication. Some computer languages handle the mechanics automatically, so the user need never become involved. That said, consider a cipher Mult128, where the message is taken in 128-bit blocks, and each block is multiplied by a secret 128-bit integer m modulo 2 to the power 128. In other words, only the low-order half of the 256-bit product is used, and the high-order half is discarded. This means that some of the intermediate products in the multiplication need not be calculated, because they contribute only to the high-order end of the product. Reaver can read the message by multiplying the ciphertext by the multiplicative inverse m' of modulo 2 to the power 128. This inverse exists whenever m is odd. Let's see how to find a multiplicative inverse. Section 15.5.1. Multiplying and dividing congruences. I promised early in this book that I would present all the necessary math as it was needed. This is one of those sections. The method for calculating multiplicative inverses involves multiplying linear congruences. Before I show how that is done, let's look at an example to see why this is an issue. I used part of this example in section 3.6. You might wish to reread that section before proceeding. Not all congruences have the same strength. Some congruences are strong and have a unique solution. Some congruences are weak and have many solutions. The stronger the congruence, the more information it gives. Consider these congruences, listed from strongest to weakest. The reason for this disparity is that in all but the first of these congruences, AX is congruent to B mod n. The parameters a, b, and n have a common factor. In 10x is congruent to 8 mod 12. The parameters 10, 8, and 12 have the common factor 2, and the congruence has two solutions. In 9x is congruent to 3 mod 12. The parameters 9, 3, and 12 have the common factor 3, and the congruence has three solutions, and so forth. The larger the common factor, the more solutions, and the weaker the congruence. When a, b, and n have a common divisor, d, you can divide the congruence through by d. For example, 9x is congruent to 3, mod 12, has a common factor of 3. Dividing through by 3 gives 3x is congruent to 1, mod 4. You can solve that by sight. The solution is x is congruent to 3 mod 4. That checks out since 3 times 3 equals 9 is congruent with 1 mod 4. To translate this result back to mod 12, the first solution is 3 mod 12, and you get the other two solutions by adding 12 divided by 3 equals 4, and then adding 4 again, namely 7 mod 12 and 11 mod 12. To recap, if A, B and N have a common divisor D, then there are D distinct solutions. The first solution is the solution to A over D is congruent to B over D, mod N over D, and the other solutions are spaced apart by N over D. Let's look at two other situations. Suppose again that AX is congruent to B, mod N, and that A and N have a common divisor that does not divide B. For example, 3x is congruent to 7, mod 30. Then the congruence has no solution. Suppose instead that A and B have a common divisor D that does not divide N. Then you can divide A and B by D. For example, if 10x is congruent to 25, mod 37, then 2x is congruent to 5, mod 37. This can be solved in your head by adding 37 to 5, making 2x is congruent to 42, mod 37. Dividing by 2 gives x is congruent to 21, mod 37. Just as you can divide a and b by a constant, you can also multiply a and b by a constant m. That m must not have a common factor with n. In other words, m must be invertible modulo n. Otherwise you will make the congruence weaker and lose information. For example, suppose you are given 9x is congruent to 3, mod 12. This is a weak congruence with 3 solutions. If you multiply a and b by 2, the congruence becomes 18x is congruent to 6, mod 12, which is equivalent to 6x is congruent to 6, mod 12, which has 6 solutions. The weak congruence has become even weaker. You can also add and subtract congruences that have the same modulus. Suppose ax is congruent to b, mod n, and cx is congruent to d, mod n. These can be added to get brackets a plus c x is congruent to b plus d, mod n, or subtracted to get brackets a minus c x is congruent to b minus d, mod n. This can be used to strengthen a set of weak congruences. For example, suppose you have 9x is congruent to 3, mod 12, and 8x is congruent to 4, mod 12. The first congruence has 3 solutions, and the second has 4 solutions. If you add them, you get 17x is congruent to 7, mod 12, which reduces to 5x is congruent to 7, mod 12, which has the unique solution x is congruent to 11, mod 12. Even smarter, if you subtract the two congruences, that gives brackets 9 minus 8x is congruent to brackets 3 minus 4, mod 12, which gets you directly to x is congruent to 11, mod 12.